Alright, hello my wonderful students. This is the last foldable of section 6.2. This one's rationalizing the denominator. So this is what we talked about in the last foldable, like whenever we have a radical in the denominator, trying to get it out of the denominator. So let's get to it. Alright, so the first part that we have here is our cube root of 5x squared divided by 12y squared z. So the easiest way to put this is basically we're kind of just going to ignore the numerator. Well, let's because this is this way, we're going to split it just like how we put everything underneath the same radical. We can actually take everything out of the same radical as well. So we're going to leave it as the cube root of 5x squared over the cube root of 12y squared z. So all we did is we reversed the process that we did in the last video. And we're doing that only because we need to rationalize the denominator. So we're going to rationalize the denominator. Denominator. Sounds so evil, that word. Denominator. Alright, so the easiest way to do this, or I guess the only way to do this, is to break down the 12 into primes. So let's do this right now. So we have our 12, and our 12 is going to be 4 times 3, and our 4 is going to be 2 times 2. So we have a 2 squared and a 3. So we're going to rewrite this equation using this here. So we have the cube root of 5x squared divided by the cube root of, instead of writing 12, we're going to write 2 squared times 3 times y squared times z. This is the tricky part. In order to get this out from the denominator, we have to multiply by a number that can take the cube roots out. Okay? So normally, when you rationalize a square root, you would just multiply both numerator and denominator by what's on the denominator. On this one, we can't do that. It's a little different. I'm going to show you why. In order to do that, we are going to have to multiply by a cube root. But we're going to have to multiply by a cube root that will let us take everything out. For an example, if I have 2 squared, in order to get 2 cubed, which is what I need to pull everything out, I need to first get another 2. So because if I had 2 cubed, that would work. So I'm not going to multiply by 2 squared here because that would make it 2 to the 4th power. What I'm going to multiply is by 2. Multiplying this by 2 would mean that if I had 2 squared times 2, this would be 2 cubed, and 2 cubed will come out. But whatever I do in the numerator, the denominator, I have to do in the numerator as well. So this is also by 2. Okay. 3 to the 1st power is going to need 2 more copies of 3, so 3 squared, in order to pull it out, because 3 to the 1st power won't come out in the cube, but 3 to the 1st power times 3 to the 2nd power would give me 3 to the 3rd power, which would come out. So also doing the numerator again. This one here is y squared. So in order to get a third one, I need a third one over here. And I have z here, so z to the 1st power. So I would need 2 more copies of z in order to take it out. Okay, that being said, okay, so I'm going to show you what this looks like here when I do the math, right? Because I can do the math here. So basically, this is not really changing the thing because this is just multiplying by 1. Because even though we multiply by this crazy thing here, it's this over itself, so it's still just multiplying by 1. Okay, equals. So, all right, so once again, okay, so we got to find it's kind of finding the perfect factors for the perfect cubes. Okay, so the numerator is going to be, what color did I pick? Green. The cube root of 5 times 3, I'll just write it out, 5x squared times 3 squared, I forgot the 2, times 2 times y times z squared. Okay, and in the denominator, we're actually going to have all the wonderful pairs that we need. We have 2 squared times 2, so it's going to be 2 cubed. 3 to the first power times 3 squared, so it's going to be 3 cubed. Y squared times y, which gives us a y cubed. And z to the first power times z to the second power, which is going to give us z to the third power. So now we know everything in the bottom is cubed, so everything in the bottom can come out. And then we're just going to kind of rewrite the numerator and then get it all sorted. So let's do that first. And I'll explain what I did right here. So let's go ahead and do the numerator first. What color did I pick? I picked blue. Oh, let's pick black. So we have the cube root of 5 times 3 squared. So 3 squared is 9. Yes. So 3 squared, I'll just write them out. 5 times 9 times 2. Then we have x squared times y times z squared. And on denominator, these all come out, so it's just 2 times 3 times y cubed, times y times z. So everything came out, which is perfect. That was what I wanted. 5 times 9 is 45 times 2 is 90. None of these can come out because we saw here that they don't have primes to come out. So this is going to be the cube root of 90 x squared y z squared over 2 times 3 is 6 y z. This is going to be our final simplified answer. Okay, and the reason is because, so for this one, the radicand R-A-D-I-C-A-N-D, sorry for my wonderful writing, in the denominator needs, and the numbers we had was, we needed a 2, we needed a 3 squared, we needed a y, and we needed a z squared to make, what did I say? We need to make the perfect, make factors of perfect cubes. So we needed to multiply this here. That's what we did here. So we needed to multiply this here in order to make the factors of perfect cubes. So if we did here, so in order to take it out, so we can rationalize the denominator. So even though the numerator still has a cube root, it doesn't matter because we don't have one on the denominator anymore. Okay?